And actually, I already added a few things because I was thinking about what you might need to know. So, I defined astronomy already. It's studying anything that originates outside of Earth's atmosphere. Okay. Um, just as a kind of a general definition, we're going to totally kind of start doing that. Um, and you should, I mean, obviously, one of the main things that we study are stars. What's fascinating about the history of our planet is almost every culture has tried to make sense of what they're seeing in the sky at night. What I find a little bit discouraging is we don't look at the sky at night so much anymore because we have too many other distractions. There's like your phones and like videos and movies, and it's like, oh, who's going to go look at the sky at night? It's like, and even if you try it in town, if you live in town, um, you don't see a whole lot because of light pollution. So a lot of it's not that accessible because all the light from the street lights and everything in other people's houses sort of obscures what you would see. But if you live out of town, and you guys probably appreciate the sky a bit better at night because it's impressive what you can see. You should just know what a constellation is as in a general sense. That's where we group stars to form shapes. The classic one you're probably familiar with, at least in our hemisphere, is the Big Dipper, which is a cluster of like, what is it, 7 stars, I think, 3 on a handle and 4 in the cup. Um, yeah. Um, the but the Big Dipper actually points, or at least yeah, I think it's 3. It's like 1, 2, 3, and then there's a cup. Actually, maybe there's only 2. Now that I think about it, there might only be 2 on the handle, and then no, I think there's 3. I think there's 3. Anyway, the point is it makes the general shape of a cup, and then these last 2 here actually point at the North Star, which is Polaris. That star is pretty much right above the rotating axis of Earth, which is why it appears not to move at night. But in terms of a clustering of stars, the Greeks are the ones that really gave us all of the constellations, but they're not the only culture that did that. But that's the one that kind of stuck in the general culture, especially if you study astronomy in English. So I want to just quickly talk about a star in general. And there's 2 things I want you to know about a star. So in this picture, it just shows the core, the interior, and then there's also an atmosphere on the surface outside. And this is showing our sun. What I want you to start getting a sense of here is gravity. Gravity is actually, I'll just draw one arrow here. Well, maybe, yeah, I'll just draw one and label that FG. Sorry, I don't know if you can see that too great. Gravity is trying to pull everything in, okay? So there's the mass of the gases and everything that's on the outer part of the star. Gravity is trying to pull it in. But inside every star, there is a process called fusion. Okay, and you'll see that in this video. Fusion is happening in the center of the star. A lot of that's being driven by, well, actually, all of that's been driven by gravity. Gravity is pulling things together in so strongly that atoms get close enough together that they will fuse, and you'll get primarily helium, you'll get hydrogen fusing into helium. We're going to cover that in a second. That's off on the right. So, but when fusion happens, that actually releases energy in the form of radiation. And so there is actually a force outwards. Basically, and we can just call it radiation. Okay? But it's radiation energy. And it actually is exerting a force. It's like there's explosions happening inside the sun and they're like radiating outwards. These 2 forces for a star are usually in balance. Usually gravity is being, like the gravity that's trying to pull everything in is being balanced by this radiation energy that's trying to blow everything apart. However, as the star goes through its life cycle, eventually the radiation energy runs out. And you'll see why in this animation. I'll show you in a second. But eventually and it depends, first of all, the star has to form in the first place. Okay, so we're going to get to that towards the end. But gravity will just pull hydrogen gas that's just out in the universe. It'll start to attract it in clumps. And then you get a bunch of it, and then that attracts more. And over a long, long, long period of time, you'll get a bunch of hydrogen that gets pulled together by gravity. And as soon as there's enough of it, then the gravitational force becomes so strong it triggers a fusion reaction, and that's actually when a star lights up. That's when it starts to produce light. Prior to that, it's just matter. It's just clumps of matter coming together. It's not doing anything. But as soon as the fusion reaction starts, then it starts to emit light and heat and all the other forms of radiation we've been studying. And when that gets out of balance, though, at the end of a star's life, essentially it explodes. Okay, so the radiation energy dies, and the gravity pulls everything. It pulls, well, basically the innermost parts collapse, but the outermost parts get thrown out in what's called a supernova. And we're going to see. First off, though, I want to show you where this radiation energy comes from in the first one. And this is nuclear fusion, okay? So this is where you join smaller nuclei to form a larger one. And this one does release energy. So I'd like you to add this. I'd like you to just say plus energy at the end of this reaction. But what I need you to understand is the parts of this reaction. This is going to come up a little bit later when we study nuclear energy, but it's good for you to start seeing it now. You guys might recognize these. What do you think H is? What does H stand for? What is it? Hydrogen. What's He? Helium. The point is here, this is called nuclear annotation, the way we're writing this. The top number here, I'll maybe label it over here. This top number, it's kind of like, it looks like a superscript and a subscript, which is technically what it is. Here, I'm going to make some space here. We can get rid of the Big Dipper. This is called a nucleon number, okay? And nucleon is a general term meaning proton and, let's say it's the number of protons and neutrons combined. Okay, protons and neutrons combined. So that top number captures the number of protons and neutrons. This bottom number, though, in this type of annotation, this just shows the number of protons only. Okay, so what this is saying is this is a hydrogen atom. You guys already caught the H part. It has one proton, which also confirms that it's a hydrogen, but it has two nucleons. So what that means is the two refers to it's got to have at least one proton, because we already counted for that. And the other particle is a neutron. So you'll see this arithmetic is we won't do too much of it just yet, but it's good for you to start thinking about it. If you have two nucleons, you can find the number of neutrons by going 2 minus 1. You take the top number, subtract the bottom number. So really what this is, and I can sketch it off to the side, this is a hydrogen atom that has one, actually I'm not going to label it, let's just do a P plus, and N0. Those are the symbols for protons and neutrons. P, the lowercase p with a positive means it's positively charged. N, of course, is the neutron, but the 0 means it doesn't have a charge. So it's P plus and N0. And then orbiting that nucleus is an electron. Okay, so this is a very simple atom: one proton, one neutron, and one electron. The catch here is, though, the way we write this nuclear reaction called fusion. You show which two particles fuse together. And so in this case, if I have two hydrogen atoms that look like this, what happens is you make helium, and you make a certain type of helium, which I'll cover in a second, but then you also make one N. This N stands for a neutron, okay? And these numbers have to add up in terms of the arithmetic, okay? So if you can see here, the top numbers, we have 2 and 2, and then over here you've got 3 and 1, okay? So the top numbers have to add up together, which they do. And then look at the bottom numbers. They have to add up as well. So 1 and 1 become a 2, okay? Now, what we're saying here basically is the total number of nucleons has to stay the same in a fusion reaction, in any kind of reaction. It's a lot like chemistry, but this is a nuclear reaction, this one, okay? And the bottom numbers also have to add up, okay? So that's why this number is a 0, because a neutron is not a proton. So in the proton numbering convention, this guy would have a 0, but the nucleon number for a neutron would just be 1 because it is a potential nucleon. You'll see really quickly that these numbers have to balance. But the other thing that's fascinating about this whole process is it does release energy. So this is how stars actually start making energy, is by a nuclear fusion reaction. So listen, actually, I'm going to let me quickly switch to this. What I want to show you here, this is a video of what's called a neutron star. Now, a neutron star forms at the end of an average star's life. And a neutron star is called that because it's so concentrated with neutrons, okay? Basically, it's compressed under huge amounts of pressure, and it's almost like an atom core that's just full of solid neutrons, okay? So there's a bunch of stuff in here that's not necessarily, you don't have to necessarily know, but I do like how it summarizes the fusion process when a star first forms. And this video also talks about those opposing forces. Gravity's trying to pull a star in on itself, but the radiation pressure is pushing out. And those tend to stay balanced. So anyway, let's see if I can get this guy to start. Okay, here we go. Let's see if it'll. that's right. Okay. So, actually, this picture right here, this is what I want you to be thinking of when we talk about stars now, okay? Because a star will have both of these forces at play. And later on, when we get to the end of this section, we'll follow the life cycle of a star, and it's largely determined by which one of these is strongest, okay? Because over time, I think this one starts to be, this one starts to overpower the radiation pressure when the fusion reaction kind of kicks out. Oh, the other cool thing is inside the hearts of stars, iron is the heaviest element that you can fuse, which is really weird because there's way more elements on the periodic table than iron. Iron's like number 26. There's like 100 and whatever elements on the periodic table. So where do all the rest of those come from? Well, when a star explodes, all that extreme pressure when it explodes in a supernova or just a nova, that creates the pressure necessary to make all the other elements. So I've heard it said that we're actually, like you and I, we're actually made out of stardust. And that's technically true because when a star explodes, all those heavier elements are made, like past iron. So like lead, uranium, gold, silver, all of those are made when a star explodes. But it also explains in part why potentially there's a lot of iron in the universe. In fact, the Earth is the dominant metal that makes up the core of the Earth is iron. It's molten iron. Okay, element number 26 for some reason. But there's reasons why that element is the most stable element out of all the elements. But it's kind of weird. You wouldn't think that. You look at the table, you're like, well, I don't know which one's the most stable. It turns out it is iron. Iron is the most stable element in the universe. So here, actually, wait, let me pause that and let's get back to the notes. An example on here, you can add it if you want, but we're going to get to it soon anyway. The other type of nuclear reaction is called fission, okay? Fission means splitting, like fissure is a crack, okay? Or like the root word for fission is to separate. Nuclear fission is splitting. This happens though with large nuclei. So you have to start with a very big atom that's not stable, and it will want to split on its own and make smaller nuclei. Okay. So there's really two routes you can take with elements in the universe. They either want to join in terms of fusion or they want to split. Um, both, though, release energy. I kind of emphasize that in both of these here. This process releases energy, and this process also releases energy. Both types release energy. In fact, if you know a little bit about the history of the Second World War, the Second World War ended in Japan with the dropping of atomic bombs. Those were nuclear fission bombs. Okay, they used uranium and I think plutonium for one of them. Okay, but since the Second World War, both the Russians and the US have developed weapons that don't use fission, they use fusion. Those are called hydrogen bombs, okay? And those bombs are ridiculously more powerful than the fission bombs. As crazy as those fission bombs were, the fusion bombs are even worse. Thankfully, those hydrogen bombs, they're literally called hydrogen bombs because that's what they're doing. They're fusing hydrogen to make helium, but on a large scale, and it releases ridiculous amounts of energy. None of those have ever been used on civilians, fingers crossed. That's what the whole Cold War was. If you guys studied that in your social studies classes, that was all about the nuclear weapons, both in Russia and the US. But those were fusion bombs. They both are very useful if you can do them safely and not for the purpose of war. Anyway, I showed you this reaction down here. You're welcome to copy it if you want. This is actually the reaction that happened in the fission bomb that was dropped in the first one was Hiroshima. Yeah. Second one was Nagasaki. Hiroshima was the first one. So this is the reaction that happened in that bomb. It uses uranium, but it's an isotope of uranium called U-235. 235 is the nucleon number, and 92 is the proton number. Okay, so if you look up uranium on the periodic table, it's element number 92. There's an intermediate step that I cut out, but what happens is it breaks up into one of the possibilities. There's actually a number of possibilities as best I know. But the main possibility is that uranium would break up into barium. This is barium, sorry. I could write that here. And this one is krypton. Yes, the Superman element. Sorry. So, oh, and then it also makes 3 neutrons. Okay. And what's a little scary about this, you guys have maybe heard of a chain reaction. This produces neutrons. Those neutrons can go hit other uranium atoms and make them fission. And it happens like very quickly and in succession. So if you've got a whole bunch of uranium, it can basically all go off in a few milliseconds if you do it right. Okay? If you want to release all that energy at once, which is what the bomb was. The point here is, and you'll start seeing this soon, all of these numbers balance. Okay, so I start with 235 in the top row of numbers, 141 plus 92 plus 3, that equals 235. Okay, so there's a total of 235 nucleons on the right-hand side of this arrow, and then the other one is there's also a total of 92 protons, or 92 positive charges, but yeah, let's just say protons. 56 and 36 will give you 92, okay? So you'll see shortly that, or not shortly, but we get to the next unit in energy, we're gonna be balancing equations like this. The arithmetic isn't too hard, but I'm just giving you a sense of the difference between fission. Oh man. I was gonna sneeze, but I am, there. And yeah, for everyone who got that recording, I'm sure that would sounded lovely. Okay, so but just know with stars, it's fusion that we're dealing with. It's fusion that we're dealing with. Okay, something else you need to know generally about the sun. Let's go back to talking about our sun. Yes, it's a fusion reaction. The surface of the sun is not the hottest location. Okay, so if you look at this, you can see that the surface of the sun's only 6,000 degrees. That's roughly the equivalent, or this is where we get visible and infrared light, is with those temperatures. What I want you to see, though, is the correlation between temperature and the type of radiation. As the temperature goes up, actually, where is the hottest temperature? I think it's, yeah, the solar flare is, I think, by quite a large margin. This is 10 million degrees Celsius. That's pretty hot. But I want you to correlate with that really high temperature. That's where you get the high energy radiation. Okay, X-rays and gamma rays. Radio waves are not high energy, but they also do come from that region. But X-rays and gamma rays, those are coming from the areas of the sun that are the hottest. And as you get down to the relatively cooler temperatures, like 6,000, it's like, yeah, 6,000 degrees, that's cool. That's not very hot. I'm like, yeah, it is. But anyway, the higher energy radiation comes where there's higher temperature. And I think I kind of said that off to the side here. Yeah, layers of atmosphere generate higher energy radiation. The layers of atmosphere are higher than the surface. Okay. Now there's charged particles they're being generated here, and they just get thrown out away from the sun. That is called the solar wind. It's literally a physical wind of charged particles that's coming away from the sun, and they're thrown out and they hit all the planets. Okay, so and actually at the edge where, if you're outside of the sun, our sun, if you get far enough away from it, you don't detect those charged particles anymore. And if that's where you are, you're actually outside of the solar system. I think that's partly what defines the boundary, is where in space, if you get to a point where you're no longer experiencing the solar wind, you're not in the solar system now. You're like in no man's land, or you're like approaching another star or something. Okay, because every star has a limit to its kind of influence in space, and once you pass that, you're no longer in the system. you, you've been booted out of the system. Yes. So solar flares, actually I think there were some in the videos we watched. It's kind of, the sun has different cycles of activity. There's times where the sun isn't really doing anything, but there's other times where it's very active, and the nuclear reactions are causing radiation pressure that's just kind of belching off the surface. And these solar flares can be like hundreds, if not thousands, of kilometers in length, and they're just bursts of charged energy and radiation coming out of the sun. They definitely generate the gamma rays. That's what this is talking about, a solar flare. The higher energy types of electromagnetic radiation come from solar flares. They actually can disrupt communications here on Earth. because there's enough energy that when it hits our radio and television antennas, it can disrupt them briefly. So we can, even though we have a magnetic field, we can still feel that influence. Okay, outside of that though, this is stuff I'm confident you can reference if you're asked questions about the sun's surface and also about the kinds of radiation that are coming off the sun. But again, this was a quick introduction to fusion and fission. So look, if there's no questions, let's go on to the next page. This one, in fact, I'm not sure where the color kicks in. Oh, there is a bit of color on this page, I think. This table right here is a good one that affirms the nature of the atmosphere. And I know it's not easy to read, so I'm going to try and clarify it. This is showing the electromagnetic radiation spectrum from basically radio waves on the left all the way to gamma and cosmic on the right. Okay? If you're not able to read that super well, I think you can kind of make it out, but I'll try and blow it up. So this one says, what do we talk? Solar wind, X-rays. Yeah, okay. So over here we have X-rays and gamma rays. And on this side, you've got radio waves. Okay, so visible light is kind of in the middle. What I need you to see though, this diagram shows these arrows coming in. If the arrows don't make it to this bottom line, then they don't pass through the atmosphere. So that line I'm kind of emphasizing, I just drew it. That is the Earth's atmosphere. The long wave radio waves are actually absorbed by the atmosphere, so they don't get in. And then there is a little blip. What's that in here? Radio. Oh, infrared. There is some infrared that actually gets through, but most of the other, like the wavelengths just below the visible light, they don't get through. But this here is basically from infrared to ultraviolet. Okay, so there's infrared here. You got visible light in the middle, and then you have ultraviolet on the end of that little speck. Okay, I'm kind of blowing it up on purpose. The point is, though, those rays of energy will reach Earth. Those are going to hit the Earth's surface. But because of the ozone layer, so I'm going to write the word ozone in here, it's largely responsible for blocking everything after that. So we talked about UVA and B, and essentially UVC. UVC is actually blocked by ozone, and then everything above that is. So X-rays, gamma rays, those don't make it to the Earth's surface because of ozone. We'd be in a lot of hot water, as I mentioned before, if that wasn't blocked. We'd have much higher incidence of skin cancer for sure. Okay, like all organisms would really struggle because everything's adapted on our planet to not be hit by that stuff, and it's because the atmosphere is there. So if that was suddenly gone, we'd be in trouble. So effectively, I think that's what I said here in this text below. Yeah, from UVC up. Yeah, so all the high energy electromagnetic radiation from ultraviolet C and up through gamma rays is absorbed by the atmosphere, as well as the long radio waves at the beginning. But all the other stuff actually makes it to Earth. And we're glad for that because you want to be able to see stuff. If visible light was blocked, that would be kind of dark down here. Mostly it's ozone. I wrote ozone in there. Don't forget, though, that there's other gases in the atmosphere that also help. Water vapor is a classic one. But then there's methane and carbon dioxide, okay? Kind of the scientific community has been a little more focused on the carbon dioxide because the argument of human-induced climate change. But there are other gases that are a lot more significant than carbon dioxide for sure. So before we go too much further into studying space, I need to quickly cover some properties of light that you should be generally familiar with. There's no math with any of this, but you just need to be generally familiar with how this works because you're going to have to be able to explain, initially, you're going to have to be able to explain telescopes, okay? So let me just blast through these quick. The first one is reflection. Visible light as a wave definitely exhibits reflection. And what reflection is, it's defined. It says the angle of incidence is equal to the angle of reflection. This picture over here captures what reflection effectively does mathematically. And I just didn't put the angles in here, but you can add them if you want. This would be theta number 1, okay? The angle from the ray to what's called a normal, okay? This is actually just a perpendicular reference. But that angle, if ray of light hits a plane mirror, it will reflect back at the same angle, okay? So you have theta 1 and theta 1. Those two angles are going to be the same. And it's just like, a bounce pass in basketball, or you hit a hockey puck off the boards. You're going to get the same angle that you came in at, and that's what reflection is, okay? So visible light does that. Visible light also does this cool trick. It's called refraction. Visible light is actually made up of more than one color of light. Isaac Newton found this out, and you guys have maybe seen it if you have cut glass in your house, like in your doorway. If sunlight hits it just right, it'll refract it into a rainbow of colors, okay? So this is showing a glass prism. White light's coming in on the left there. And then the different colors actually travel at slightly different speeds, which means they exit the glass prism at a different angle. And that produces Roy G. Biv. No shocker. But this is what happens in this concept of refraction. I'm going to zoom in on this because, yours isn't in color. Sorry about that, but maybe you can still track what's happening. In this picture, what we have are wave fronts, okay? And what you need to see here is this distance between a dotted line and a dotted line. That is a wavelength, lambda, okay? That's a distance between one wave front to the next one, or from crest to crest, if you will. And in this substance, whatever it is where we're first starting here, you would also have you would have some form of velocity. We'll call that V1, okay? So this wave is traveling at a certain velocity, and it also has I guess we could call this wavelength 1, just so you can make a distinction. Now watch what happens though when this wave hits a different medium. So we could say go from a classic one. Let me just label this. Let's call this air, and let's call this one water, okay? And light does this as you move from one medium to another. As you approach the more dense medium, which is water, there's a part of the wave that hits the water first, and I'm going to highlight that in green right there, okay? So what's happening is these wave fronts are coming in, but then this part of the wave, this part of the wave hits the water before that part does. And as soon as light hits a more dense medium, it slows down. So that actually slows it down, and it causes it to change direction. So the medium was initially headed somewhere like this, and then it hit the wave hit the new medium, and it bent, and it changes direction. Now, there's a bunch of other stuff that happens. I'm not going to have you do the math for that. But the main one I want you to see is what happened to the wavelength. Now that we're in water, look at this. The wavelength now, you can see that it was big here, but now when you get in, the wavelength is smaller. So wavelength 2 got smaller because the wave itself has actually slowed down. So V2 I'm going to draw just a smaller arrow, okay? So the velocity of the wave actually slowed down in the water, and light actually does travel slower in water, okay? So, but refraction is the bending of light as it passes from one medium into the next, okay? And did I say that? Yeah. Oh, yeah, I did right here. Light traveling at an angle from one medium to another will bend and change direction. Okay, so that's refraction. The next one is diffraction, and then I also put in interference. So you're going to see this when we start, when we look at narrow openings. If you are sending waves through an opening, what starts to happen as the opening gets smaller is this phenomenon of diffraction. So this one shows low levels of diffraction with a wide opening, but if you get a really narrow opening, then the waves will actually bend away from, they'll kind of bend outwards from that opening in all directions. It looks like a loudspeaker, okay? It's broadcasting a signal, which is actually what happens. And the truth is, these wavefronts actually circle all the way around they would circle all the way around and hit the barrier even, like something like this. So you're basically making concentric circles or circles that share the same center, and they're going to radiate outwards from that opening. Now, waves do this. This is definitely a characteristic of waves. But this process here, and you can label it if you want, this is called diffraction. So this is where a wave that's normally traveling in one direction, if it enters a very small opening, then it diffracts, and now it scatters in kind of outwardly, radially, in all directions from that point. Okay. Is there anything else you need to say on that? No, that's probably good for now. Okay. If you guys are good, let's go to the next page. This one actually shows interference now. Okay. So diffraction happens when light passes through a small opening. So if you want, you can label diffraction as occurring right here. Okay, that's where diffraction is happening. But what's really cool is these waves now, they start to overlap and interfere with each other. And so you see this kind of crazy pattern that starts happening where you have crests and troughs from the wave are meeting up in different places. What that causes, though, is areas of brightness and areas of darkness on a screen that might be placed behind the. Oh, sorry, this one already said interference pattern. Sorry, it said that at the bottom. But in terms of the wave properties, diffraction happens at the narrow openings, and then interference happens if you happen to put a screen there or observe these waves colliding and intersecting with each other. Yes. So the interference pattern that's created, you get areas of brightness and areas of darkness, and they kind of scatter in that regard. That's right. I can show you that using a laser, and let's keep going. The last one is polarization. Because light is a wave, it actually has crests and troughs, and it's usually vibrating it's usually going in all directions, okay? Like as it's generated. Long time ago, we figured out ways to actually filter that. And so if we apply what's called a polarizing filter, so it basically has vertical, or it has filters all in one direction, and this can be down at the molecular level, we can stop the light that's not vibrating up and down and reflect that. And so then the only light that gets through is the light that's vibrating in the same plane as the filter. We've gotten really good at this. We basically make all of our sunglasses with polarizing lenses. Okay. This is showing a cool picture of the Inuit in the north. They came up with a way to cut out snow, to remove snow blindness. I don't know if you guys have ever heard of that. If you get exposure to too much sunlight from the reflection of the sun on snow, it can give you a headache. It can trigger migraines and stuff. It's too much light for your eye to handle. They figured out that if you take a piece of whalebone or like a rib and then cut horizontal slits in it, and then you wear those over your eyes, this cuts out a good portion of the light, and so it diminishes your chance of getting snow blindness. But we've obviously got more modern methods. It's really easy to show you too. I've got two polarizing lenses here. These are for a camera, and it's meant to cut the light down. But if I layer them on top of each other, then rotate them like this, well, I guess you can kind of see if I rotate them just right, eventually I get to a point where they block the light. So it means that the planes of these horizontal planes, if I line them up like this, so one is vertical, the other one's at 90 degrees, I'm going to block all the light. Okay. So if you keep rotating these, you can see it gets dark, and then it gets light again, and then it gets dark and light. And I can even do that here with this screen. What's crazy is the light coming off of my screen. If I rotate this, look at that. Okay. So this way the light's coming out, but then I rotate it this way and I'm blocking it. And so the light coming off of this screen is polarized. It's coming out in one plane, but with a filter, I can actually block that. What's crazy with these filters, I'll maybe pass these around. You can actually block your phone with it. So if you hold your phone up and you look at your phone through this, actually, if you turn it, you can actually get different colors because it's actually messing with, or it's actually polar, or it's affecting the light that's coming out of your device. I'll just pass these around so you can look at it. And actually, that's true too. Some people have noticed if you're looking at your phone while you're wearing sunglasses, if you look at it in just the right way, it's hard to see because the light coming off your phone is already polarized, and you're sending that through sunglasses, which are also polarized. And so, yeah, you're gonna kind of block things. So, all of that's a big crash course to understanding what happens in a telescope. So the simple thing here is you just need to know the difference between kind of two different telescopes. The initial ones made by Galileo are what made him famous. He was the first to actually start looking at planets, and he did it using lenses. Now, what happens is if you basically take a large lens and a small one, like this picture shows, and what's happening here is refraction, okay? So I'm going to maybe write that word up here. This is I mean, you might even say it's a refraction telescope or a refracting telescope. Light comes in and it hits the glass and it gets bent. So the light changes direction as it goes through the lens. He's actually using two different styles of lenses, which is totally fine. Oh, thanks, Miles. Then what you can do is focus the light, and you can see objects at a greater distance, at a great distance. You can see them more clearly. Oh yeah, there's another one too, if you guys haven't seen it yet, sure. Johannes Kepler was another astronomer. He actually he used two lenses as well, but he used a slightly different shaped lens. But both of them were successful in enlarging objects that were very far away. So the first type of telescope that you should be able to identify is a refracting telescope. And the reason why it's refracting is because it's using lenses, okay? So it's using glass, yeah, using glass in the form of a lens. That's different though from the next one. So if you guys are good, just go to the next page. Isaac Newton was the first to realize that he could make an even better telescope if he used mirrors, not lenses. And the only problem you should note about lenses is that thicker glass causes distortion. So that's why you don't make large lenses. If you're limited with how much glass, like how thick the glass you can make a lens. If you're trying to make a bigger and bigger telescope, you hit a certain limit, and then the image gets distorted. It gets blurry. It doesn't stay focused, and so you're limited if you're only using lenses. However, if you use a mirror, you can do this. You can accomplish the same effect, but you can use mirrors as big as you want. Okay, make them as big as a tennis court or bigger. Okay. So Newton was the one, and if you looked at a diagram of the incoming light rays, they're reflecting off of a mirror. As soon as you see that there's a mirror somewhere in the telescope, we don't consider it a refracting telescope. We consider it a reflecting telescope. So I maybe put that word up here, okay? Because we're using that property of light that it will reflect off of a shiny surface. And in this case, yeah, there's a plane mirror and a convex lens. So there's some other things that will help get the image to your eye. But the biggest telescopes we have on Earth are not refracting telescopes. They're reflecting. And probably the most famous telescope that we've ever known is the Hubble Space Telescope, at least for visible light. Okay. And actually, maybe tomorrow I'll show you a summary of the Hubble Space Telescope. It was launched in the 90s. It basically is out of the Earth's atmosphere, so there's no distortion from the Earth's atmosphere, and it's able to study the universe from outside of our atmosphere. Okay, and then send the pictures back to Earth. So there's some pretty fascinating things that we've learned from Hubble. But Hubble isn't the only telescope. We've launched so many telescopes into space now. The most famous one, I think, is the James Webb Telescope. Everyone's pretty excited about that one because of what it's been finding recently. So let's just end today on this last little property of light, and the principle is called resolution. if you're looking at two stars that are very close together, um, if your opening is very small, that's what's showing on the right. If you have, or sorry, wait, I got to go backwards here. Source one and source two. This is the light sources, and if you send them through a very small opening, on the screen, those light waves overlap significantly. Okay, and it's difficult to resolve the two objects and recognize you're seeing two objects and not one. That's really the kicker with resolution. Low resolution means you can only see large features, so you can't differentiate. So it's like you have difficulty differentiating between two close stars. But if you have high resolution, you can see the small details and you can easily distinguish two stars that are close together. Okay? So this is a lot like microscopes. Microscopes have the same problem. You want to have high resolution in a microscope so that you can differentiate between two really small organisms, say on a petri dish or something. Okay, so they don't look like one dish, they don't look like one organism, but they look like two. So this is a property of a telescope. A good telescope has high resolution. Okay. Um, the other text surrounding this sort of reinforces that idea, but I wanted you to at least understand that as we got going with telescopes, the better telescopes became reflecting telescopes using mirrors, and that also gave us the ability to have higher resolution as well. We can actually, if you're looking deep into space and you see a bright light, is that really a single star, or is there two stars that are one's behind the other and you just can't tell? Um, it's really helpful to be able to resolve the difference between two objects. Okay. Um, Actually, wait, we've got. You know what? I think I'm going to pause this here.